So I want to apologize if there will be some mistakes in my language. The topic of my presentation is for general public. I presented it for a younger audience here, for younger students, and the topic is quantum world, quantum computation, quantum computing, and quantum simulations. So at the beginning I said something about quantum mechanics, some brief introduction to this subject, and at the end we will back to the classical simulations about the quantum system. This is the research area of my PhD studies. So let's start with the quantum world. We have here some funny cartoon. This is actually this cartoon comes from the paper of Wojciech Żurek, the supervisor no supervisor, a leader of Bartek in Los Alamos. And this is funny cartoon. It shows us the border between a classical world and quantum world, because these two worlds are completely different. So let's start with the classical world. The classical world is, everyday life world, where objects are always in the same state, in some definite state. So a classical object has this property that if I have some material object, it is always, for example, in a precise position, in space. But for quantum objects, there is a little difference, and I pointed here two major differences between quantum and classical worlds, two major features of a quantum world, and this is discreteness. And so maybe let's start with discreteness. It is rather intuitive. It is also amazing, but it can be understood. So discreteness is about portions. So the name quantum is a synonym of portion. And for example, if we had some atom, like a hydrogen atom, and we have a proton with electron, this electron can only appear in some portions of energy. We call it energy levels, and if we want to excite this electron, we have to put some exact portion. It cannot be arbitrary. And other portions are the quanta of matter. For example, the quanta, it is the synonym of particles. So the matter is in portions like electrons and other fundamental particles. And also the light, the electromagnetic field, has also quanta, which we called photons. Okay, but this is very amazing feature, but for quantum computers, the most important is quantum coherence. And quantum coherence is about in general, it is about superpositions. So, as I said before, microscopic object can always is in some definite state, like a position state. But in quantum mechanics, we also have something what we call superposition, and the quantum state can be in two states simultaneously. So it is completely unintuitive. We have, for example, an electron which can be in the state like in here, in this position, and in another position in the same time. So this is superposition, and it is at the heart of the quantum computers, of the quantum computing. Okay, so let's start with this property. We have a superposition. We call it, we use in quantum computing a very simple system, which is a qubit. A qubit is a system which has only two states. It could be labeled by the arrow, the up arrow and the down arrow. It could be labeled by 0 and 1 with analogy to the classical bit. We also use in classical informatics a bits which has two states, 0 and 1. And in quantum physics, the situation is different because the qubit can also be in a superposition of these two states. And in mathematical framework, we add these two states, but there is a very important feature that we can add these two states with different signs. we know from school, you probably know about two signs. This is plus and minus. The other audience has also know about other signs. This is the generalization of the sign, which we call the phase. And phase can be present by this pen. I use this pen to show you what is the phase. A phase is just an arrow. It shows some direction. It is not a direction in our real space, in three-dimensional space, physical space, but in some abstract space, and it is just a direction. So you can imagine that plus sign is a direction, is that direction, and minus sign is a direction, opposite direction. And we have the whole branch of other directions. And we can add these two states, this 0 state and 1 state, for example, with different directions. So now I should use other hand. I have also another pen. Okay, so we have a state, a position state here, and we have another state, a position state here. And these states can have a different signs, a different phases. And how it looks like. If I draw these two arrows, and if they are in the same direction, we call that they are in a phase. So they add together, and we call it constructive interference. So, but what it means? It means that if these two states interfere constructively, that they increase probability to finding them. So if they are aligned in a phase, then it increases a probability to find a system in this state. But if they align oppositely, so if they have an opposite direction, then they, so we can add these two things and give a bigger arrow, okay? So this is a constructive interference, but if we add those two arrows, then we have a destructive interference and we have 0, no arrow. Okay, so maybe you know these equations. These are very, very important equations in school. In Polish we call it wzory skróconego mnożenia. In English it is just probably a square of the sum. And these equations, we can have plus or minus here, and we have a squared plus b squared, and this is a mixed term, and this mixed term is an interference term. So if we have a plus sign, if we add these two arrows in a phase, then we have some additional part. It increases the total probability, but if we have a minus, like here, we have the destructive interference, and we have this something which we have to subtract from the total probability. So these equations are very important. They are also used in quantum mechanics, so you should learn it. Okay, so this is superposition and interference. And this is the basic idea to use this superposition to make a quantum computations. So let's go to the quantum computing. This is some realization of an algorithm, because what we do when we want to make a quantum computation, we have many different states, like D-wave have many different states. It can have a state 0, 0, 0, 1, 0, 1, 0, 1, and so on, many different states. And we search for some specific state, which is our answer. It's a correct answer. All the other states are incorrect answer, are wrong, and only the one is what we're looking for. So, and we have these arrows. Any of the states have some specific arrow, okay? And at the end, we want to, and so we can plot it in okay, so maybe stop in that. So any of the states have an arrow, and then we want to make some quantum computing, some quantum evolution to increase a probability of our correct answer and decrease all of this probability and decrease the probabilities of all of the incorrect answers. And it is shown at my presentation that we start with some, this is the initial state, then we make a superposition equally probable superposition. So there is our answer. One of these states is our answer, correct answer, and all of the other are incorrect. So at the beginning, we make a global superposition. We call it a global coherent state. And now we start to making a quantum computing, some evolution, some physical interaction. We can do it by lasers or something, some external fields. And then we saw that these states interfere with each other. And some states increase, their probability, their existence is increased, and other states are decreasing. So as we know, now we go to the other steps in our computation, and at the end we have only one solution, and this is the correct solution. We suppose that this is correct solution, but as you see, there are some finite probabilities for other solutions. So as it was said, that quantum computer is always probabilistic. We should set up the same situation once and once again, and only after many times we can find a correct answer. So these are the basics of quantum computing, and at the end of this presentation I hope you something learn about quantum mechanics and quantum computing. Maybe one more note about it. This is completely another approach than classical computing, because if we want to do it classically, then we should check all of these solutions once one after another. So it is sequentially. This computing is sequential, but here we have at the beginning all of the solutions. So this is the power of superposition. Then that we have all of the solutions at the same moment in the beginning of our computing, and only we should to extract from this whole set the correct answer. So it is very amazing, and probably it is a future of computing at all. And at the end, I want to say something and advertise to specialists the quantum toolbox for quantum computing. This is a toolbox written in Python language. Python is a very, very nice language. It is very simple. So, I use this quantum toolbox, which is called Qtip, to make quantum simulations. Of course, I do it on a classical computer, but using this toolbox, we have a whole branch of fine things, like we have the old algebra of linear spaces, so we have the representations of vectors, we can do inner products and so on. We have a tensor product, which the representation of tensor product, which able us to make a simulation of composite systems. Firstly, I should say that this quantum toolbox is especially for open quantum systems. The open quantum systems are very important in a context of also in context of quantum computing, because the most disadvantage or most barrier for build a quantum computer, the biggest barrier of building quantum computer is the coherence process. It's an interaction with the environment. We should our system should stay in this coherent state. So decoherence is losing this state. and many other things. Especially the very fine thing is a spin algebra. We have predefined all of spin matrices in any dimension. So it is very nice. So thank you for attention. Thank you.